Okay, guys, this is resonance. Okay, as we can see in the figure here, it is stated that when the blade vibrates at one of the natural frequencies of the string, large amplitude standing waves are created. So what happened here is actually we found that if a periodic force is applied to such a system, the amplitude, okay, the amplitude of the resulting motion of the string is the greatest when the frequency of the applied force is equal to one of the natural frequencies of the system. One of the natural frequencies. So meaning that in the system we have a few things, or a few, for example, here in the figure we have the string, we have the vibrating blades, we have the wall, and yeah, we have the machine itself. So combine all of them to be a system, and this phenomenon is known as resonance. Okay, that is resonance. Next one, we have standing wave in air columns. Okay, this is columns. We have columns, and this standing waves is actually the sound wave. Sound wave. So as we can see here, we have two types of system. The first one on our left, or figure A, is the system with open at both ends, and another one in figure B at our right is the system with close at one end, meaning that we have air column open at both ends, and another one in figure B we have air columns with closed at one end. Okay, for your information here, as we have already discussed before about the node, anti-node, so here we are applying the same concept, node and anti-node. If you still remember the node, where is node, where is anti-node? So node is the point where the amplitude is zero, and anti-node is where the system is having a maximum amplitude. Okay, sorry. We are now in this figure. It is comparing. Displacement wave and pressure wave. Displacement wave and pressure wave. And right now, let us focus on the displacement wave. Displacement wave. From here, we can have, or we can produce, or we can define the equations to find harmonics, to find the frequency of one segment, two segment, three segment, and segments that we require or we need. Okay, as we can see in the figure A, starting from the first one here. Okay, this is the first harmonic of air columns open at both ends. So let me write down here. This is open at both ends. This one close at one end. Okay, so as we can see, the shape of the standing wave is different if we compare between open at both ends and close at one end. Okay, I think let us focus on the first one, open at both ends. Okay, guys, we are taking into consideration the length of the tube, or columns here, air column. Air column is like a tube. It's like a tube. Okay, this let's consider the distance here. The length of the tube or air column is equal to L. So all of them with the length of L. Okay, now this one is similar concept with what we have in standing wave or on the string. Okay, so let's see here. We have also A here representing the antinode. This one is node and this one antinode. So meaning that at open ends of the column, we will have antinode. Okay, as we can observe here, at all open ends, we have antinode. Same goes to the another case here. Yes, on our right, close at one end, we have at open end, we have antinode, which is the maximum amplitude. Okay, the point where the amplitude is maximum. Okay, so from here, this is the first harmonic. Okay, first harmonic or fundamental. Okay, first harmonic or fundamental. So as we can see here, this is the distance of L right now is from antinode to antinode. So as we recall the previous one, distance from antinode to antinode will be equals to L equals to 1 over 2 lambda 1. 1 over 2 lambda 1. Okay, so this is what we have in the previous one, which is standing wave on a string. Okay, in our case here, we are going to have lambda in terms of L. Previously, we have L in terms of lambda. So we have, in our case, for first harmonic, lambda 1 will be equals to 2L. And our frequency, same as before, we have F1 equals to V over lambda 1. So V equals to V over 2L. Okay, right. The second one for second harmonic, also the same. The distance between the distance from open end to the other open end is still L, but in terms of lambda, we have equals to L. In terms of lambda 1 here, just now is 2L. And for the second harmonic, okay, let's have the second harmonic here. Lambda 2 will be equals to L. Okay, why? Because here we divide this one. Distance from, okay, write down here. I just write down here. Distance from antinode to node will be equals to distance from node to antinode, which is equals to 1 over 4 lambda. So 1 over 4 plus 1 over 4. So same goes to here. Antinode to node, and node to antinode, and antinode to node, and node to antinode. So we have 1, 2, 3, 4 segments. So it will be basically equals to lambda 2 equals to L. So for frequency of the second harmonic will be equals to V over L equals to 2 F1. 2 F1. 2 times F1. Okay, if we times 2 here at the first harmonic, we will get this equation. Okay, if we times 2, if we times 2 here, 2 times F1 equals to 2 times V over 2L, we will got here, we will obtain V over L, same as this one. Okay, right? So for the third harmonic, we have to apply the same thing. Same thing. So if we not sure about the L and the lambda, we can refer back to what we have previously. Okay, and then another case, we can have we can draw, we can illustrate. For example, this is the shape of the first harmonic. Okay, first harmonic. The second harmonic will be double of the first. This is the second harmonic. This is the same as what we have here. If we are going to find the third harmonic, then we have to draw again the shape of the fundamental. So we have 3 fundamentals equals to third harmonic. 2 fundamentals equals to the second harmonic. So here we have first harmonic. This is first harmonic also. This is first harmonic also. Fundamental, fundamental, fundamental. For your information again, first harmonic is actually same with the fundamental. Okay, right. Okay, and then for the third harmonic, lambda 3 will be equals to, so if we have here lambda 3 equals to 2 over 3L. Okay, right? And F3, third harmonic, will be equals to 3F1 equals to 3V over 2L. Okay, alright guys, yeah. Okay, this one is for standing wave in that column for open at both ends. Let's take a look another case which is closed at one end. If we are going to have we are going to find the second harmonic, the third harmonic for close at one end, we can use this method also by drawing the shape of the fundamental. Okay, but this one is a little bit different here. For open at both ends, all harmonics are present. Unlike we have close at one end, we have only odd harmonics present here. If you can see, this is the first harmonic, fundamental, and then the second one will be third harmonic, the second consecutive. The third consecutive will be fifth harmonic. Why does that happen? Okay, if we use drawing to draw, this is the shape of the first harmonic. Okay, let's say we add another one, another first harmonic. This is actually the same with what we have in the open at one end, open at both ends, sorry. So we have to add another one. So meaning that here we have 3 times fundamental, 3 times fundamental. So 3 times fundamental will be equals to third harmonics, which is the second harmonic, the second consecutive harmonics after the first harmonics. Okay, alright. The first harmonic here, or fundamental, the lambda. Okay, this one also the same. The length of the tube, the length of the air column is also the same, equals to L. So what we have here, the first harmonic. Remember, this is the distance from antinode to node is 1/4 lambda. So we have here the first harmonic, lambda 1 equals to 4L. Okay, and F frequency is coming from same concept as the previous one. F1 will be equals to V over lambda 1 and equals to V over 4L. Okay, no need to memorize the equation, but you have to understand the concept and the situation. Okay, if you are memorizing, then it will be confusing. It might confuse you. Okay, and then we go to the second harmonic. What do we have in the second harmonic? it is actually not the second harmonic but second consecutive. So meaning that here it is not second but it is third harmonic. The second consecutive. Remember this one? Third times fundamental. So it is third harmonic, which is the second consecutive. So meaning that here we have lambda 3. Lambda 3 will be equals to 4 over 3L. And the third harmonic F3 will be equals to 3V over 4L equals to 3 times F1. So 3 times F1, we got this fish-like shape. Okay, and then the third consecutive harmonic here will be the fifth harmonic. Fifth harmonic, we have 5 times the fundamental. So we have lambda 5 here equals to 4 over 5 L. Okay, so L, this L is because of the length of the air column is equals to L. And we have F5 here will be equals to 5V over 4L will be equals to 5 times the fundamental. Okay, and the general equations for both, we have general equations for both. For open at both ends, all harmonics are present. We have Fn equals to nV over 2L equals to nF1. So n here representing all harmonics 1, 2, 3, dot dot dot. And for the second case will be Fn equals to nV over 4L equals to nF1, and n representing the odd harmonics only. Okay, this is a close at one end. Another one, the green color there, open at both ends. This is actually the we can call this is the general equations, the general equations, and these two equations is coming from the one that I have shown, that we have discussed just now with this one. Okay, right. So that is standing wave in air column. And last but not least, we have beats. Okay, beats. What is actually beats? Beats is actually interference of wave in time. It will cause if the waves interfere in time, it will cause a phenomenon called beats. Beats are slow. Actually, the beats are the slow envelope around two waves that are relatively close in frequency. Okay, as we can see here, this is the figure. The figure is showing that the beats is actually formed by the combination of two waves. Okay, figure A. Figure A is actually this one. Figure A is actually two individual waves. We have the green color and the blue color. And figure B here is actually the combination of those two waves. Combination of those two waves. Okay, the envelope. Remember the envelope before? So this is the envelope, the dotted line. Okay, represent the beating of the combined sounds. So to calculate the beat frequency, we have the equation of F beat equals to modulus of F1 minus F2. So this is beat frequency. This is because the amplitude varies with frequency, and then the number of bits per second is called the bit frequency. Okay, so that's it for our chapter 17. So we will discuss the tutorial questions soon. Thank you.